Not that glorious. Okay, so I'm going to review a little bit before we get into all of the other phases of matter. We know that matter has the capability of changing from one state to another. So we're talking about our solids, liquids, and gas phases here. States of matter, phases of matter, you can use either one. So for instance, looking back at our particle arrangement here. Gases are spread apart. They're moving very fast. They are in constant random motion. Okay, they're bouncing off the walls of their container, filling the container completely, causing pressure on the container, and that's how you know there are gases in there. The liquid, they're kind of close together, but they still have more freedom, more movement, more kinetic energy. Gases have the most kinetic energy, the energy of motion, because the particles are moving so fast. Liquids have some kinetic energy. They're moving around a little bit more. They take the shape of their container, but they don't fill it completely. Whereas the crystalline solid structure, they're in fixed positions. They vibrate in place. They still have energy. They still have a little bit of kinetic energy. The only time a particle wouldn't have any kinetic energy at all is if it was at absolute zero, which is 0 Kelvin, negative 273 degrees Celsius, super, super cold. Okay, we don't really get down there to 0 K, even though they've tried to simulate it in the lab. Okay, and they form a nice orderly structure. So some of the characteristics here are listed, but remember, the solid has like attractive forces between the particles holding it together, or it wouldn't be a solid. Those attractive forces are like glue holding the particles together. The liquid has some of those attractive particles, so that's why it's somewhat held together, but the gases do not have any particles, therefore, any attractive forces. That's why they are free, random motion, so they're not attracted to each other at all. In order to change phase, you have to either break these attractive forces or you have to reform the attractive forces. So if we're going from a solid to a liquid, we need to add heat energy to break some of the attractive forces so that the molecules and the particles can spread out. Now, if you're going from the liquid to the gas phase, you have to break all of the forces in order to get them into that gas phase so that they can bounce around and not have any attractive forces between them. If you're going the other direction, where you're taking the gas and you're condensing it into a liquid, cooling it down, making it slow down, the particles slow down and they get closer to each other and they form these attractive forces. So that's where you get more of a liquid phase, where they're kind of attracted to each other, filling the shape of their container and all that. And then if you're going through the freezing phase, where you're going from liquid to solid, basically they cool down, they get really close together, and they reform those attractive forces, and they form now the solid, which has its own definite shape. Okay? Doesn't have to have a container now because it has its own definite shape. So that's what we're talking about now when we're changing phase, by the way. Entropy, remember, is a measure of the disorder or randomness. I don't know if we got this far on our paper. So, disorder or randomness of the particles that make up the system. Gases are pretty disorderly. They're going everywhere. They're hitting the walls. They have high entropy. Whereas solids that are a nice orderly crystalline structure, these guys have very low entropy. The liquids are kind of in between because they have a little bit of freedom. And we're talking about degrees of freedom and most variance possible. So most very possible positions. So gases have lots of possible positions they can be in. Solids, however, on the other hand, don't. Okay? The universe tends to go towards randomness, disorder, more variations. So, in which order does the entropy decrease? Solid to liquid to gas, or gas to liquid to solid? Gas to liquid to solid, our entropy will be decreasing. You're making it more orderly. And oh, by the way, because the universe goes towards randomness, putting things in order takes energy. And you have to expand energy to keep things in order. So it's kind of like fighting against the randomness of the universe. And that's why a lot of times to make sure like our rooms are cleaned up and other things. Like we have to put energy in, we have to put things away, we got to keep it in order. Okay, so keep that in mind. All right, so now let's take a look at our heating curve. We're going to label a bunch of things on the heating curve. The first thing you're going to label is the first horizontal area. This first horizontal area, okay, you're labeling this on your heating curve. This is when the solid is warming. Okay? Our kinetic energy is increasing. So, the orderly structure of the solid, those particles are vibrating, but they are now being given energy, so they vibrate more and faster and so forth. Therefore, they are able to eventually get to a point where they have so much kinetic energy. At this point, they're going to start breaking apart and start phase changing. So eventually, they start vibrating fast enough to where they get enough energy to where they can break apart. When they start breaking apart, this is in this solid to liquid phase change going on here. This part you have mainly all solid. Over here at this end you have all liquid. In between, at that point, you're going to have half solid, half liquid. Like if you were melting an ice cube at this point, the ice cube would be smaller and you'd have a pool of the water that the ice cube was sitting in. That would be what you would see here at this central part of the graph, this part, okay? So the flat one here is the first phase change. As you should see, the temperature is not changing. The temperature stays the same because the temperature is not trying to make the particles go faster. It's trying to reposition the particles. So this is where we would say that the potential energy is increasing. We're repositioning those particles, giving them a new energy arrangement. Now, I'm sure you guys have heard of potential energy in terms of physics terms, where you're at the top of the roller coaster, you're sitting at the top, that gives you the highest potential energy, getting ready to go down. Okay? Here it's the same idea, except for we're positioning our molecules and our particles differently. We're spreading them apart, so now they have more energy due to that. The next one, anybody want to take a guess as to what the next slope would be following our trend here? What could be that next slope? The liquid is warming. Okay, this is where the liquid's warming. So your kinetic energy again, the kinetic energy is going to be increasing here. So when you put a pot of water on the stove to start boiling, you turn on the stove. Is it instantly boiling? No, right? You'd understand that. Instead, you have to sit there and wait because the liquid molecules have to warm up. They have to get moving faster. They do eventually get to a point where they've gained enough energy and they're moving fast enough where they can start breaking away. So when they have gotten to that point where they can start breaking away, we're up here, getting ready to start turning into the gas. Okay? So we're just warming the liquid, the kinetic energy is increasing, the particles are speeding up. Now, what do you think the second plateau might be? Changing it to a gas. So this is where we have the liquid gas phase. So if we're boiling the water, we're talking about boiling water. So here we're all at all liquid. Over here we're at all gas. In between, this is where we have like half liquid, half gas. Okay? So you're ready to make your pasta and you put your pot of water on the stove and it finally starts to bubble. When it starts to bubble, okay, if you left it there, what would happen? It would eventually all boil off and you'd be all the way over here. Okay, but of course, we're trying to make pasta here, so we wouldn't let it all bubble off, right? We'd stick our pasta in just to get it cooking. Okay? But if you just left it there, heating away, eventually all the water would go away and become water vapor gas. Okay? So once again, here's like 50% liquid, 50% gas at this part on the phase change. And also notice that the temperature is not changing. Instead, the energy is being used to reposition the particles and to break apart those forces holding it together. The forces holding it together, they have to break those. That's what the energy, the heat energy, is being used for. And last but not least, what is that last slope going to tell you? The gas is now warming. Gas particles, you can make them speed up and move faster. So we have over here the gas warming, and you're also increasing its kinetic energy, making it move faster. Okay? It's moving faster, it's bouncing off the walls of the container more, and you get higher pressure. So if you want to think about it in terms of like whether heat or cold, warming up a gas, in the wintertime, our tires usually do what? Anybody know? They deflate a little bit. But in the summertime, what happens? They inflate, and if you have the pressure gauges, you would see, because in the wintertime, it's colder, the gas isn't moving as fast, so it's not hitting the walls as much. Whereas in the summertime, it's really warm, so the gas is hitting the walls and you have nice, good pressure. So sometimes in the wintertime, you have to add some more air to your tires, whether it's bike tires or car tires. Okay? Now let's look at the phase changes themselves. So going from the solid to the liquid, this one's going to be melting. You already know that one. That one's easy though. Right? You know melting. Going from liquid to gas, you've probably used the word boiling before. But now we're going to start using the more complicated term of vaporization, meaning vapor is a gas. So we're turning it into a gas. Now let's go the opposite direction. If we wanted to change the gas into a liquid, what would we call that? That's called condensation. Now in this case, you're slowing down the particles, getting them close together so they can reform some of those attractive forces, changing it back to the liquid. And if we wanted to go from the liquid to the solid, it is called freezing. Once again, getting them slowed down enough so they're really attracted to one another, and now you get that solid with the definite shape. So now I'd like to show you, this is a really good heating curve. So this one, I like the way that it's drawn because not only do you see the curve here, you see the curve, phase change, you see the phase change here, but at the top here you also see the positioning of the particles and the movement of the particles. So here you have your solids vibrating in place. Here, you have like half solid, half liquid. You can see that the liquids are spaced a little bit further apart, but they have a little bit more motion. Okay, here you see just the liquid where it's warming and then the particles are spread apart. And then over here our gas change. So you have lots of gas and then you have your liquid still floating around. That would be about the midpoint. And then last but not least, you have your free-flowing gas particles the way that they're moving. So this one's very helpful in looking at those particular, not only the curve itself. You don't really need to concern yourself with the like MC delta T yet or the delta H fusion yet, but you need to definitely understand every part of the curve, what's going on at every part of the curve, and what the particles look like at each phase, their characteristics. That's all important stuff for the quiz. All right, a few other things to note. If you know your curve here, you can always go over from the plateau to figure out the melting point. The melting point and freezing point are the same value. For water, it's 0 degrees Celsius. You can always also find the boiling point, which is also going to be the condensation point. If you go over from the plateau, you should be able to figure out the boiling point or condensation point. And for water, it would be 100 degrees Celsius. Those are the main ones there. Boiling point, melting point, freezing point, condensation point. These are those phase changes, those actual temperatures at which these things occur. All right, looking at our cooling curve on the back. This one's on the back. It's basically the same idea, except for now we're starting over here in our gas phase. We're cooling it down. This would be condensation. Going that direction. Then we would be cooling down the liquid. This is the liquid cooling. And then we would start freezing it to eventually turn it back into a solid. And the solid would be cooling. You could keep cooling down the solid. So it's really just opposite of a heating curve, called the cooling curve. The other one's called the heating curve. Good. Now for the states of matter. There's 3 states we're looking at: solid, liquid, gas. Plasma is a little bit too complicated, so we're not going into that. Melting, vaporization, condensation, and freezing. These 4 you pretty much probably know from, 5th grade. You've been taught these over the years multiple times. Physical science and everything. Melting and freezing, opposite directions for the solid-liquid combination. Vaporization, condensation is the opposite, or they're the ones for boiling and condensing. Okay, going from the liquid to the gas phases. There are 2 others. Does anybody know what the 2 others are? Sublimation. Anybody heard of it?
This one, solid goes directly to a gas.
Solid goes directly to a gas. It's sublimation. Solid goes directly to a gas. Deposition's the opposite. The gas goes directly to the solid. Now, they skip the liquid phase entirely. There's a really good example of sublimation around Halloween time. What do we see? That makes that nice smoky fog looking stuff.
Dry ice.
Dry ice, thank you. You set out the dry ice and it sublimates and it makes that white foggy. Yes, and that's, dry ice is just frozen CO2. It skips the liquid phase and goes right into the gas. The other one for deposition is not as fun because there aren't a lot of great examples of deposition, but airplanes way up high altitude, atmosphere where there's lots of water vapor while they're flying, the water vapor can directly solidify onto the wings. They call it icing of the wings. So that would be an example of deposition. Now for the phase diagram. The phase diagram looks like a Y. Hopefully you catch the Y pattern here. Here is its middle point, this part of the Y, this part of the Y, and then here's the little stem of the Y. What you need to pay attention to is there's temperature and pressure on this particular diagram. Okay? So we're not just considering temperature in terms of phase changes, pressure does play a role. Phase diagram is a graph of pressure versus temperature. That shows in which a phase can substance exists under different conditions. So at high pressures push things together. So they make, the particles get closer. Those attractive forces form. So that's why you see over here in the high pressure area, this side of the graph, you see a lot of your solids. Okay? Really high pressure is going to make it get close and have those attractive forces. You're going to be in that solid phase. Liquid kind of in the middle, and the gas over here. At very low pressure and high temperatures, you're going to see lots of gas. And each of these is a phase change line. So this one, okay, is going between the solid and the gas. That's why we have sublimation and deposition there. This one's going between the liquid and the gas, so you see your condensation and vaporization. And this line, as you can see, there's multiple melting and freezing points along this line, depending on the pressure and the temperature. And then over here, there's multiple boiling points and condensation points. And here, the same thing for the deposition and sublimation, depending on the pressure. Okay. The next thing we need to concern ourselves with is I'll come back to that, is the triple point. This part where all three, the middle of the Y, this spot, that's known as the triple point. And that is where all three phases coexist, or they're in equilibrium. So you have all three of them happening all at once. And in a minute, I'm going to show you a little short video with that. Up here, too, one thing to note, this part between a gas and a liquid is called the critical point. And this is where we have something called supercritical fluids. The pressure gets so high that it's trying to push them together. The temperature is also so high, so it's trying to make them speed up, so they're trying to stay far apart. At that point, we're kind of in between the gas-liquid phase. So there is a little bit of gray area. Not everything's always definite. At really high pressures, really high temperatures, we have these supercritical fluids. It's kind of like an in-between phase. Okay? So right now, I'd like to show you a quick little video. Okay, so if you take a look here, watch what's going to happen now. This round bottom flask is actually attached to a vacuum, so it can suck the pressure out and make it exactly what the pressure should be at the triple point, and the temperature is also what it should be at the triple point. So if you see up here, you're going to see, is it playing? No, it's not playing. You're going to see, so this is now simulating the triple point of cyclohexane at the right pressure and the right temperature, but it has to be at both exactly or it won't happen. Up, now we see solidifying. Now we see some bubbling. Bubbling means gas coming. Bubbling, oh, there we're back to liquid. Now it's solidifying again. Bubbling gas. So you see all three phases are occurring at once here. And it keeps going, and so we'll keep just changing back and forth from solid to liquid to gas, solid to liquid to gas. Okay, back to this point. Melting, let's review. Melting is always going from what phase to what phase? Solid to liquid. Vaporization is going from what phase to what phase? Liquid to gas. Good. Sublimation. Solid directly to the gas. Good. Deposition. Gas to solid. Condensation. Gas to liquid. And freezing is liquid to solid.